In this video, we are going to implement the transient pipe flow scenario with an inflow at the left edge as well as an outflow at the right edge, such that we then see the boundary layers creating transiently as well as over the length of our pipe. And then we also see the hagen-poiseuille parabolic profile being created at some point in our simulation. Let's get started. Hi and welcome to this new coding video with Python and NumPy. As said in the intro, we're going to solve a pipe flow scenario, so an interior flow scenario, transiently with an inlet and an outlet boundary condition. By doing so, we will see boundary layers due to the viscous effects of our Navier-Stokes equations. We will be solving the Navier-Stokes equations on a staggered grid with finite differences, you could almost call them finite volume, an explicit Euler time stepping, as well as a so-called P2 pressure correction scheme, which is quite similar to the simple algorithm that you might have heard. Here I've listed again the momentum equation as well as the incompressibility constraint. We are living in two dimensions, therefore we have two momentum equations, one for the u velocity component and one for the v velocity component. Let's look at our scenario. As said, we will have a pipe flow scenario. That means we have a rectangular domain where the x-axis represents the longitudinal axis alongside our pipe and the y-axis is the perpendicular axis, think of it as the cross-section of our pipe. And our pipe or tube has wall boundary conditions, which are no-slip boundary conditions. That means our u velocity component and our v velocity component is 0 at the top edge and at the bottom edge. At the left, we prescribe an inflow. That means we have a Dirichlet boundary condition on our velocity. The u velocity component is set to 1 uniformly over the length of this edge, and the v velocity component is set to 0 uniformly over the edge. At the right end of our domain, we have an outflow boundary condition. Outflow in that case is associated to the fact that we don't know the distribution of velocity or pressure at the right end. So we will assume a 0 gradient in the u and v velocity normal to the outflow, which is the x direction in that case. And this makes sense if we assume that our domain is long enough, then the flow is fully developed, which means it does not change over the x-axis anymore, and therefore its derivative will be 0. Initially, we will prescribe a uniform velocity in u over the entire domain with being 1. So we have a velocity being 1 at each point in the domain, and we will let the v velocity be 0, and you can also see that by the fact of the horizontal velocity arrows that you see in this particular example. And then, as you've also seen in the intro, the expected outcome is that we have this parabolic profile developing over time as well as over the x-axis, in a way that after a certain point our flow is fully developed, so it has this parabolic profile and does not change anymore, such that our outflow boundary condition assumption also holds. And I've tried to visualize this here, that we start off with the uniform profile in the beginning, and then slowly the arrows that are closer to the boundary or closer to the wall are getting smaller due to the viscous effects and the no-slip boundary condition, and consequentially, the arrows in the center have to get larger since we have an incompressibility constraint, which means we can't lose mass flux. Interestingly, this hagen-poiseuille profile is one of these rare cases where you can actually solve the Navier-Stokes equations analytically, so we know by these derivations that the parabolic profile is the one that we should be expecting here. How do we discretize our equations? The naive approach would be to use a so-called co-located grid, which you've also seen in previous videos of mine. And the idea there is that we just take our domain as it here is, so think of this being the channel or the pipe represented discretely with 3 elements in y direction and 6 elements in x direction. So here in that case our domain is twice as long as it is high, so we have an aspect ratio of 2. And then in a co-located grid, we would use, for instance, the vertex nodes that I've indicated with the plus here, and save all our variables there, which means the u velocity, which is in x direction, the v velocity, which is in y direction, as well as the pressure. And for some applications, this might not be a bad idea and can actually also lead to correct simulation results. However, here, due to the fact that our flow is strongly driven by a pressure gradient, we would observe a pattern that is called checkerboarding pattern. And the problem with the checkerboarding is, or the fact why it arises is, imagine for instance this node here, and you want to compute the pressure gradient for this point, and you use a central difference approximation, which is a second order accurate approximation to the first derivative. And this one would only involve this point, which is to the right, and this point, which is to the left. So in case you do an approximation to the x derivative. And the problem here is that the derivative for the point itself does not include the point itself. And this could then yield a checkerboarding pattern, because for instance, assume here we would have the value 50, and here as well, and here you have the value 100, then alongside this axis, you of course have a gradient, so you of course have a derivative. But our central difference approximation would yield a zero derivative due to the fact that the value itself is excluded. And then if you think of a checkerboard, you see, or chessboard, you see that you have these white and black patches which are in this certain pattern, and this kind of pressure field could develop on a collocated grid if you don't take particular care. There are some measures against that, but in a naive collocated grid that would happen, and here in that case it would happen for our simulation. So we need to find a remedy. And there are two ways out of it. One is usually referred to a Rao-Chow interpolation, which is a little bit more complicated. We will use a so-called staggered grid. And this now might be a little bit mind-bending, but you have to bear with me. The main idea of the staggered grid is to save all three primary unknowns, so the velocity in both direction as well as the pressure, at different points in our domain. For this, let us look at the following sketch. So we again have our mesh here. You see that by the fact that we have our pluses here. But now we staggered the u velocity, the y velocity, and the pressure. And you can see that here by the upwards pointing arrows, we indicate the places where we store the y velocity, so v. By the rightwards pointing arrows, we define the positions at which we save the u velocity. And then by these dots, we define the positions where we save the pressure. So originally everything would have been at the pluses, but we move the upwards pointing arrows or the y velocities half an element length or half a cell length, however you want to call it, to the right. We move the rightward pointing arrows half an element length down, and we move the pressure half an element to the right and half an element down. And if you've seen finite volume discretizations, you would say that the pressure is cell-centered because it is now in the center of this cell, whereas the velocities are on the faces of the pressure cell. And again, to remind you that we are still looking at the same domain, we have the zeroed on here, which indicates the origin of our coordinate system, which has stayed the same. So we have kept our original mesh, but our velocities and pressures are a little bit offset with respect to the mesh vertices. And for our implementation in Python, we have to now understand that the shape of the arrays in which we save our primary unknowns has changed. Before, here in that case, with 1, 2, 3, 4 rows and 1, 2, 3, 4, 5, 6, 7 columns, we would have simply used an array which is 4 by 7 in order to save each of the three primary unknowns, so u, v, and p. However, here, for the staggered grid, we see that for the rightwards pointing arrows, we only need 3 rows, but still have 7 columns. So here we would have a 3 by 7 array. Whereas for the upwards pointing arrows, we would have still 4 rows, but we would only have 7 columns, so a 4 by 7 array. And for the pressure, we have a 3 by 6 array. So in more general terms, if we have ny discretization points in y direction and nx discretization points in x direction, then we would need ny minus 1 by nx nodes for the u velocity and ny by nx minus 1 nodes for the v velocity and ny minus 1 by nx minus 1 nodes for the pressure. However, the problem with that approach is that it is now really difficult to prescribe the boundary conditions because, remind yourself, this here and this here is the wall of our domain, and here we have the inflow and there we have the outflow, and we have to prescribe the boundary conditions at each of these edges here. So the remedy for that is to introduce a padding of another layer around our domain of so-called ghost cells. And that one would look as following. So now we have our original domain with the extent given here by these special signs that you can see here. These are the vertex nodes that define the original mesh, so these ones here. And in there we have everything unchanged. And we now added another line or a padding of pressure nodes just outside of the actual domain, as well as the corresponding staggered values. So at the top here we have the staggered values in x, and there we have the staggered values in y on this right end here. And we call them ghost cells because they are outside of the domain, but you can also consider them some sort of a finite volume cell. And now the big catch is that this also changes the size of the arrays that we save, because we now allocate arrays for u, v, and p that contain all these degrees of freedom here. So in other words, we now have u velocities that take an array of ny plus 1 by nx. So we can also look at that. Let me mark that here. So we have 1, 2, 3, 4, 5. So instead of having one less, we now have one more in y direction, but we keep the same amount in x direction, which was nx. Then for the v velocity, here we keep the amount of components in y direction, which is 4, but instead of having one less than the number of discretization points in x, we have one more, and so on and so forth. So for u, we have now ny plus 1 by nx, and for v, we have ny by nx plus 1, and for the pressure, we have ny plus 1 by nx plus 1. And I'm pretty sure if you've never seen this before, this might now seem really mind-bending. And it will probably also take some time in the beginning to get your head around that. But the advantage for this mesh is that if we are now, for instance, assuming we want to compute the pressure gradient for this velocity in x direction, then this would involve the pressure to the left and the pressure to the right. And we still have a second order approximation to the pressure derivative, and we don't have the checkerboarding. That's the big advantage here. And we will see in the implementation that some of the derivatives might be a little bit complicated in the indexing, but I will try to go back to this particular plot here as often as possible in order to remind you what we are doing for the implementation. Now let's finally look at our solution algorithm. And this one looks as following. As said, we will use a so-called P2 pressure correction scheme. P2 is some sort of a taxonomy of pressure correction schemes. A P1 scheme is usually referred to an operator splitting in which we leave out the pressure gradient from the momentum equation and just solve for a pressure correction in the end. However, the P2 pressure scheme includes the pressure gradient in the momentum and still solves for a correction in the very end, which is quite similar to what the simple algorithm is doing here. And in our particular case, the P2 scheme is advantageous because we have a strongly pressure-driven flow where we need the pressure gradient in the momentum equation. Either way, let's go over the steps. First, we have an initialization according to our initial condition. And as said, for the u velocity, we want to use 1s plus the wall boundaries, of course. For the v velocity, I want to use 0s, and I want to initialize the p pressure uniformly with 0s. And then the first step is to solve the u momentum equation explicitly. For this, we say that the next u velocity, I would call this a tentative step, is the previous u velocity plus the time step length multiplied with the following components. So first we have our negative pressure gradient, then we have our diffusion, and here we have our nonlinear convection consisting of a derivative with respect to x and with respect to y. Then we do something similar for the v velocity. Quite certainly we know that the velocities, these tentative velocities, will not fulfill the continuity equation, so we have to correct them in order to be incompressible. In other words, we have to project them. For this, we will first compute the divergence, which should be 0 if it was incompressible, but it is not. And then we can use that as a right-hand side, scaled by the time step length, for a so-called pressure correction that I call Q here. And this Poisson problem with the nabla squared here is having Neumann boundary conditions everywhere except for the right edge where we have our outlet. And we will solve it using some Jacobi smoothing algorithm. For simplicity here, we can use this pressure correction Q to correct our pressure. Well, it's a pressure correction, so it shall correct the pressure. And then we see how the pressure field will develop. But more importantly, we will also use it to update the velocities or to correct the velocities to be incompressible. So we say that the next velocity u is the velocity from our tentative step that we got here minus the time step length, and then we have the central difference of the pressure correction with respect to x for the u velocity and with respect to y for the v velocity. And here again we see that the staggered grid is important, because if that wasn't a staggered grid, we might have these checkerboardings. And then the steps 1, 2, 3, 4, 5, 6, 7 are just repeated in a time loop until a steady state is reached, and we can plot it transiently to get an intuition of what is going on. And one last remark, if we want to visualize later on, we have to map our staggered grid back to our collocated grid, because that's where we define the location of our mesh vertices. And for the rest, we will consider this later, also including the stability. And then with this really long intro, I hope you're still with me here, we can start with the implementation. First things first, let us import all the necessary packages. So we need NumPy as NP for our numerical computations. Then I also need matplotlib.pyplot as PLT for the visualizations. And then I have two more optional dependencies. First, it is cmeasure, which is a collection of beautiful color maps, which we also use for visualization, as well as tqdm, which is a super simple progress meter. Then let's define some constants of our simulation. So I want to define the number of discretization points in y. And remind yourself, the y-axis, that's the cross-sectional axis of our pipe. And here I want to use 15 points. Then we have to define the aspect ratio, which means how much longer is our domain than it is high. And here I want to use a factor of 10. This one is crucial, so it has to be quite high in order to have a fully developed flow. Remember, otherwise our outflow boundary condition would not be valid. Then I want to simulate a flow with a kinematic viscosity of 0.01 with a time step length. Let me get that right here, time step length equal to 0.001, and then I want to simulate 5,000 time steps, and then I will also create a variable I want to call plot every and set that to 50, such that we only plot every 50 iterations. We also need another variable that I want to call n Pressure Poisson iterations. That will be for the equation, and that will be for the Poisson equation for the pressure correction that we want to solve, and it is fine to set that one to 50. Then let's define our main function, leave it empty for a second, add some boilerplate here by doing the name switch, if name equals main, execute the main function, and then we are sure that the file is only executed when it is run with the Python interpreter. Then let's use the endpoints in Y in order to infer the cell length, and the cell length will be 1.0, 1 meters for instance, of pipe diameter. It's quite large. You can of course also think in a different unit. Here everything is without any units. And then we divide that by endpoints Y minus 1, since we have 15 discretization points, including the 2 boundary points, which are creating 14 cells, and so we divide 1 by 14. And then let's infer the number of points in X by the aspect ratio. So we say endpoints in X going to be endpoints in Y minus 1 multiplied with the aspect ratio plus 1. So in our case, this is 14. 14 times 10 is going to be 140, and then we have 141 discretization points in X direction. Then we can define our mesh in X range by saying numpy.linearly spaced linspace from 0 to 1 times the aspect ratio, since this is going to be the length of our domain in our unitless dimension. And here I want to use endpoints in X. And then we can define a Y range by using numpy linspace from 0 to 1. And then here we have the endpoints in Y direction. Then we can use both ranges in order to create our 2-dimensional coordinates array. And this is done by saying coordinates in X, coordinates in Y, going to be numpy.meshGrid of X range and Y range. And then we could already start with our time loop, but first I want to prescribe the initial condition. So this is going to be initial condition. And for this we say we have a velocity in X from the previous iteration. And of course, when we are in the 0th iteration, previous means initial condition. And as said, I want to have a uniform distribution with ones in the velocity. So I'm going to use NP ones. And now remind yourself, we are in the staggered grid. So this one is made of n points in Y plus 1 in Y direction and n points in X direction. Because if we go back to the staggered grid and we look at our X velocities, we see we have one more than we have discretization points in Y direction, but we have the same amount as we have discretization points in X direction. And then, of course, we don't have ones on the boundary, so we have to account for the wall boundary condition. And this one is going to be a little bit more complicated now, but let me introduce. The problem here is that our velocities are not directly on the boundary. So we can't directly prescribe the wall boundary condition. So the X velocity, at least in the top edge and also in the bottom edge, is not staggered on this edge. Rather, it is staggered outside of it by half an element and inside by half an element. However, we can use an average between these two by saying the one outside plus the one inside divided by 2 has to be equal to 0, because that would be the velocity that is on the edge, and this one is prescribed to 0. And of course, then let's do some algebra magic. If we have the following, when we say outside plus inside divided by 2 equals 0, and then we can rearrange that equation, multiply by 2. This means that outside is equal minus inside. So the outside value has to be the negative inside value such that the average value on the edge is going to be 0. So in our case, that means the velocity x previous accessed at y is equal 0 or the 0th index and all in x direction. That is the fact that we are using this matrix indexing scheme. So it's a little bit unnatural that we have the x-axis last and the y-axis first, but I think you will get used to that. And here we then have to set this one to velocity x previous at 1 and then all in x direction, meaning that we set the outside value to be the negative of the inside value, because 1 means, let me show this to you in the chart here, 1 means basically this velocity, and we are setting this one to be the negative of the inside. Okay, that's long story short. We then have to do a similar thing for the top edge, and we can use -1 in order to index the last element in y direction, which would be then from the ghost cell, and then we set the value of the ghost cell to be the one of the cell just interior behind the domain boundary, and then we're good to go. So I'll remove this here, and we will use that kind of trick later on again when we prescribe the wall boundaries. Then we also have initial conditions on our y velocity. So we say velocity y previous is going to be numpy.zeros, because it's going to be uniformly 0 throughout our domain. And this one, now let's take a look again at our mesh. Here we have this v velocity, and we see when it comes to the y components, we have as many as we have discretization points, which is the variable endpoints y, but we have 1 additional in x direction. So in other words, we need an array that is of shape endpoints in y by endpoints in x plus 1. How about the pressure? And for the pressure, I want to start with a uniform 0 pressure. So I'll do numpy.zeros, and let's finally look at our staggered grid in order to see how many nodes do we have here. So for these dots, we have in y direction the number of discretization points plus 1, and in x direction we also have 1 additional. So let's go back down, and then we see this one therefore has to be endpoints in y plus 1 by endpoints in x plus 1. And then for later on convenience, I just want to pre-allocate some arrays. So let me do pre-allocate some arrays, and we're going to have velocity x tentative is going to be np.zeros like velocity x previous. And then we have something similar. I will just copy that for the velocities x at the next time step. And then let's do velocity y tentative. And the tentative is after the solution of the momentum equation. So this one is also going to be numpy zeros like, but has the y shape. And then the next is similar. With this down, we can then start with our time loop by saying for iteration in TQDM range n time steps, and then we can start with the algorithm. For this, let me go back to the doc string and look at the first step, which will be updating the u velocities. And for this, let me compute all the components individually. So we will compute the pressure gradient, the diffusion, as well as the convection. Let's start with the diffusion, since it is the easiest. So I will do diffusion in x. And for the diffusion in x, we have to approximate the Laplace operator. And for this, we will use the 5-point stencil. So let me go to the staggered grid. And now imagine we wanted to update that particular u velocity. Then the 5-point stencil is taking the direct neighbors, so this one, this one, this one, and this one, including the point itself, and has some coefficients for them. And we see all of them are equal amount apart, so we can just use the same cell length here. And that one works as following. So we say kinematic viscosity, this is the new value, multiplied with, and then we have the velocity x previous, indexed at all points in y direction. And here I will just use the interior points. Let me show that to you why I'm using them, because we are just updating in y direction, we are just updating these ones here and not the ghost nodes, because we will use the ghost nodes later for the wall boundary condition. And in x direction, I want to go one step further and say from 2 all the way to the end, which would then mean that we are, when we are at this point here, we are currently seeing this point, which is to the right of it. And then we are adding the velocity x previous at the same idea, but this time in y direction. So we are now above our actual point. So let me also add plus here for clarity. And then we do the same, but going back one step. So using the interior points in y direction, and then going back a step from the very first element all the way to the second to the last. And then the last step is to do the same in y direction. And then we're good to go. And then we just have to subtract 4 times the interior by itself to get our 5-point stencil and divide by the cell length squared. And then next step, I want to do the convection. So convection in x. So let me look at the algorithm. So we have this component here, which is the x derivative of u squared. And I want to use central difference approximation. So I'll be doing one step forward in x and one step backward in x. So velocity x previous at all points, all interior points in y direction. And then from 2 all the way to the end. And we are subtracting interior points in y. And then at x, we are going from the beginning to the second to the last element and divide by the cell length, or actually we have to do it 2 times the cell length, because if you look here and we would, for instance, look at that point, so we're doing 1 point to the right, 1 point to the left, then we have 2 times element length in between them. And then the second component in the convection is this here, the velocity v multiplied with the u derivative in y direction. For this, we will use a similar approach. So let's take a look at Staggered Grid and see here, we want to go 1 above and 1 below. So we will do, let me go down here and say this is plus. And here we have velocity x previous. And 1 above will be from 2 all the way to the end. And then we take the interior points in x direction and we subtract velocity x previous from 0 to the second to the last element and interior points in x, and we divide by 2 times the cell length. But then we also have to account for the v here. So in the best case, we would have, similar to our co-located grid, the v velocity at the same point as what we are considering the u velocity currently. And imagine again, we have this u velocity that we want to update. And then we see the v velocities are in the top left, top right, bottom left of this particular velocity. So if we take all these 4 v velocities and average them, so this one plus this one plus this one plus this one divided by 4, we would have a velocity that is associated to the same point as our u velocity. And we could use that in order to multiply it with our u velocity. So let's do that. Take a look here. So we need our prefactor, for which we use the velocity in y previous. And now let's take a sharp look. How should we do that? So if we are considering this particular point here, then we need first the top left point. And since we are considering all interior u's, we are basically only considering all of them here. And then we have to go, well, we don't have to do the very bottom line, but have to start right above and then all the way to the end in y direction. And for the x direction, we have to do all the interior nodes except for the very last one. So let's go down here and say we start at point 1, go all the way to the end. And then here at this one, we start at the first point. So which is not the first, but is the second in the indexing in Python, and go to the second of the last. And then we have something similar. So this one would be the top left point. Then this one would be the, let me get this here. Then this one would be the top right point. And here this one would be the bottom left point, because now we are starting all the way at the bottom edge and then go to the, not to the very last element, but the one before. And we have a similar thing here, which is that, and you probably see the permutation here getting some sort of structure. And then we divide that by 4 to get our average and multiply that. And then we have our convection consisting of the x derivative of u squared plus v times the y derivative of u. And then finally, we have the pressure gradient in x. So pressure gradient in x direction. And now we will finally make use of the staggered grid. So again, consider this point here. And we want to define an x derivative of the pressure. So we use the pressure point to the right and subtract the pressure point to the left and divide by the cell length. And since we only want to consider the interior nodes, we have to go for the pressure. Well, in y direction, we take the interior, so from 1 to -1. And in x direction, for the one that is right of our velocity, we go from 2 to -1. And for the one that is to the left of our velocity, we go from 1 to -2. So let's go down here. And the pressure gradient is therefore given as the previous pressure indexed at the interior in y, and then 2 to -1 in x, minus the pressure previous interior in y, and then 1 to -2. And here we only divide by cell length, because that's the distance between the two pressure nodes. And that is still a central difference. And that is probably the little bit confusing part about the staggered grid. But here we again have a second order approximation to the derivative. And that was quite a long preparation. Then we can finally update our velocities by saying velocities x tentatives at the interior, because we only want to update the interior, not the ghost values or the values that are on the boundary. Because if you look at the u velocity, you see in the top edge and in the bottom edge, we have ghost velocities. And then at the right and the left edge, we have velocities that are on the boundary. And we only want to update the interior. It's hard to highlight that, but I probably think you can imagine that here. So we just say the velocities x tentative at the interior are going to be the velocities previous at the interior plus the time step length multiplied with the negative pressure gradient, so this one here, plus the diffusion minus the convection. And then we have tentative velocities at the interior. Now we also have to apply the boundary conditions. So we say apply BC. For this, let's first start with the left and the right edge of the boundary. For this, take a look again. And here we have the advantage that in the staggered grid, the u is on the boundary, so we don't have to do any averaging, and we can directly prescribe the inlet velocity here, because we want the u velocity here to be 1. So let me go down, and then we can say velocity x tentative at the interior points in x, because we don't want to set the ghost nodes, which are associated with the wall boundary condition, and then 0 in x, because we are at the very left, and we set that one to 1. Then for the velocity tentative at the right edge, so we do 1 minus 1 minus 1. So let's take a look. And here we have a 0 Neumann condition, so a homogeneous Neumann condition due to our outflow. And so in order to get a 0 derivative here, we will just set the value that is directly on the boundary to be equal to the value that is next to the boundary. So let's do that. Go back down here and say that this value is going to be equal to velocity x tentative interior in y direction, and then minus 2 here for the second to last. And this is the left and the right edge. Now about the top and the bottom edge. So here we have 0 for the bottom edge, and then the colon indicates all nodes. And here we are basically using the same as we've also done here. We just set them to be equal to the one before, and I actually see that should be negative, of course. That is, I mean, we derived it and I wrongly set it to the positive value. So it should be negative here. And the same holds true down here, such that we can then set it to the negative value. So say negative velocity x tentative at 1 and then colon. And this will be the bottom edge. So let's do the top edge as well. Velocity x tentative minus 1 colon is minus velocity x tentative at minus 2 and colon. And that's the solution of the momentum equation in U. Now we have to do something similar in y direction. So let me just highlight that we just did it for the U velocity. So this is update interior of the U velocity. So then we can go down and say update interior of the V velocity. And we again start with the diffusion. Let's take the look at the staggered grid again. And if we are now updating, for instance, this velocity here, then the idea is quite similar. So the 5-point stencil still holds, such that we can just use the direct neighbors in a similar fashion as we've done it with the U velocity. So we say kinematic viscosity multiplied with our 5-point stencil, which is going to be velocity y previous, interior points in y, and then 1 forward in x, plus, or maybe let me add the plus here as well, velocity y previous, 1 forward in y direction, and interior points in x, plus velocity y previous with the interior points in y, and then we go backwards 1 step in x direction, plus velocities y previous, going back 1 step in y direction and interior in x. And then we subtract 4 times the velocity y previous at the interior. And finally, we have to divide by the cell length squared to get the 5-point stencil. After the diffusion comes our convection. So let's do convection in y direction. And here, let's look at the algorithm. We have, again, 2 components. First, we have this mixed component and then the derivative of v squared in y direction. So let's do that one first. And let me again first define the derivative, which will be in a similar fashion. So I think you've now seen the pattern. So for the derivative, we do velocity y previous with the interior points in y, and then going 1 step forward in x direction, since we want an x derivative, and then divide by velocity y previous in the interior in the y, and then all the way to the second to the last element in x, and we divide by 2 times the cell length. And then we have the prefactor, which is the U previous, and for this, let's take a look again at the staggered grid. So for instance, we want to update this velocity here. Then we see that we need the U velocity at this particular node. And similar to how it was for the V velocity in the U grid, in the U staggered grid, it is now for the U velocity in the V staggered grid that the neighbors that we have to average are in the top left, in the top right, and bottom left. So in order to update the interior in y, which are going to be these here, these 2 lines that we have here, we need to take the U velocities in the interior and all points in x direction, but we have to do a little bit of a adjustment here. So this will be again in y is going to be again this 1 to -2 and -2 to 1 thingy. And here it's going to be 1 to the end and beginning to -2. So the pattern we will get here is, let me go to the convection. So we have a prefactor based on velocity x previous accessed from 2 to -1 in x direction, and then from the start all the way to the end in x direction. So the first one was y direction, sorry, plus velocity x previous, and then again in y direction we are above our velocity, and then here we have all the way to the last element, excluding the last element, and then plus velocity x previous, and then 1 to minus 2, and then 1 all the way to the end, plus velocity x previous, 1 to minus 2, and then this construction here. And finally, we have to divide it by 4 and multiply with that value. And then we are only left with the v-squared derivative in y direction. So let's take a look here. For instance, we want to update that value. Then we need, for a central difference approximation, the one above and the one right below. And we are only updating the interior here. So then we get the following structure. So we do a plus velocity y previous in the y direction from 2 to the very end, and then x direction, just the interior. And then we have to square it and subtract the velocity y previous from the beginning all the way to the second to last element, excluding that one, and then 1 to minus 1 interior. And we have to square it, and I think I've probably forgotten the squaring up here. Let me check. Yes, so here you should also, of course, square it in order to get the nonlinearity in our convection. Let me see that. And then let's go down here. And finally, we have to divide this one here by 2 times cell length. And then we are left with the pressure gradient in y direction. So pressure gradient in y direction. And this one is made up of the following components. So let's go up here and assume we want to update that value. Then we need the pressure right above and below. So we have pressures in the interiors of the y's. But yeah, so it's going to be the 2 to minus 1 thingy minus the 1 to minus 2 thingy. And then we have the interior in x direction. So let's take a look here. We have the pressure previous and set 2 to minus 1 in y direction and interior in x, minus pressure previous and then 1 to minus 2 in y direction and 1 to minus 1 for the interior in x direction. And then we divide that just by the cell length, of course, because we have that staggered grid. And then let's do a similar thing in the velocity y tentative in the interior. So we say the tentative velocity is given as, or the interior of it is given as the interior of the previous velocity. And then we do plus the time step length multiplied. And here we are going to have the negative pressure gradient in y direction plus the diffusion in y direction minus the convection in y direction. And then we also have to apply the boundary conditions here. So apply boundary conditions. So let's just call them BC. Here, let's look at our staggered grid. So let's start again with the left and the right edge. And here we see that we want to prescribe the y velocity distribution at the left edge, which is the inlet boundary condition. And here, similar to what we have with the u velocities, the y velocities are not given on the boundary. So we do an averaging again, and then we say outside plus inside over 2 has to be equal to 0. And then we get the similar condition to what we had with the u velocities at the top edge, that the velocities associated with the ghost nodes have to be minus of their counterparts just inside of the domain. So let's go down here and say velocity y tentative, and then the interior points in y direction, and at point 0, since we are at the very left, so the ghost node here, this one is going to be, and now let's not make the mistake, minus velocity y tentative interior point 1. And then let's go up and check for this right point here. And now we want to prescribe the outflow boundary condition. So the derivative across the boundary is supposed to be 0. And we can define the derivative directly on the boundary by taking the ghost value of the v velocity minus the interior value and divide it by the element length, cell length, and set it to 0. And if we rearrange that, so let me go down here and do the math for you. by saying outside minus inside, like this, divided by dx is equal to 0. And then if we do some algebra magic, we can of course come up that the outside has to be equal to the inside. So again, this is for a Neumann boundary condition, and this one was for a Dirichlet boundary condition in the inlet. So in other words, we will get velocity y tentative, interior points in y, and -1 for the last point in x direction is equal to velocity y tentative, interior points, and then a -2. And let me delete the algebra here. And then we still have to set the boundary conditions at the top and bottom edge. So go up to our staggered grid. And here, fortunately, we see that these are on the wall. And if you ask yourself, how about this one here, which is not on the wall, you have to think that you can think of it as an extension of the wall. And the special thing about this velocity and also this one and this one and this one is that they are not associated with any computation. So actually their value does not greatly matter. So let's just do that in order to continue our wall here. So we set all the values here to 0, and we don't have to make any averaging since they are directly on the boundary. So let's go down here and say velocity y tentative at 0 bottom boundary, and then colon to get all of them is equal to 0. And a similar thing that can be done for the top one. So -1 colon is also 0. Then let's take a look at our algorithm on how we should proceed. So we have the second step done. Now we have to compute the divergence of our tentative velocity components. And we do that by the central differences that we've also used in the update routine. So I will call this compute the divergence, as it will be the right-hand side of the Pressure Poisson problem that we are going to solve afterwards. So for the divergence, and the divergence is going to be a quantity that is just defined in the interior of the domain and not on the ghost nodes and on the boundary, of course. So we first have the derivative in x of the x velocity component. So we do velocity x tentative, interior values in y direction, and then 1 forward in x minus velocity x tentative 1 minus 1, and then 1 all the way to the last element, excluding it. And this might seem a little strange. Let's look at the staggered grid again. So we are computing the divergence at the pressure nodes. And for this, we are taking the velocity components in the interior in y, or for the u velocity components, and going one step further, and then one step back, and then we get our divergence or the derivative here at the pressure node. So we can then divide, and we have to divide by the cell length. And a similar thing can be done with our velocity in y direction by saying the derivative is given as velocity y tentative, accessed at 1 all the way to the end in y direction and interior in x. And let me also show this to you that that's correct. So here we want to compute it, for instance, at that point. And then we take the interior values of our v velocity components, so excluding these ghost nodes here, and to go 1 up in y direction and then 1 down in y direction. So we do minus velocity y tentative 1 to -1, and then here we have the interior points. Then we can divide that by the cell length and we should be good to go. And in order to get the proper Poisson right-hand side, we have to divide that by the time step length. So I want to call this Pressure Poisson right-hand side is going to be given as the divergence divided by the time step length. And just to make you aware of this here, in case you have a different density, which is not 1, which was a simplification we did here, the density would also appear here in the multiplication. And now we have to solve step 4 or do step 4, which is the solution of the Poisson problem with Neumann boundary condition, homogeneous Neumann boundary conditions. And for this, we will be using a Jacobi smoothing procedure which is super simple, might not be as accurate as a more sophisticated iterative solver, but is definitely decent for the application here. And this works as following. First, I want to define the pressure correction in the previous iteration. So let me first give this a headline here and say, solve the pressure correction Poisson problem. And I say pressure correction previous, and now previous and next refers to the Jacobi iterations that we're going to do. And this one is going to be a zeros array, and it has the same shape as our previous pressure. And then we do some iterations. So I will just use an arbitrary variable name here, so underscore, in range of n Pressure Poisson iterations. This one was set to 50, so here we are doing 50 smoothing iterations in order to get our pressure correction. First, we will create a new pressure correction array, so pressure correction next, which is going to be a zeros-like tensor of the pressure correction previous. And then how do we do the smoothing? So basically what we have here is a Poisson problem, which has this Laplace operator, which we could approximate by the 5-point stencil. So which means that the point to the left, plus the point to the right, plus the point upwards, plus the point downwards, minus 4 times the point in the center is equal to that one. And of course, divided by the cell length squared. And we can extract the point in the center and bring all the components to the right and just apply this over and over in the hope that it will smooth the solution out or get us a solution to this system here. So let's code that down and say that the pressure correction next at the interior is going to be given as 1/4, because the value in the center has the prefect of 4. And then we have here the 4 components in our 5-point stencil which are not the center. So remember that from the diffusion that we did on the velocities in x and y direction. So I want to use previous, and then first interior in y, and then 1 forward in x, plus 1 forward in y direction and interior in x, plus pressure correction previous, interior in y, and then 1 backwards in x, plus pressure correction previous with 1 backwards in y direction and interior in x. And then on the right side, we get a minus in there because we had this prefactor with -4, which is also the reason these are positive, because they went on the right hand side. And here we then have a minus and get the cell length squared, which was in the denominator for the 5-point stencil, multiplied with the pressure Poisson right hand side. And here we don't have to extract the interior because this already is just the interior. So it has the correct shape. And then we have to apply the pressure boundary conditions. So apply pressure boundary conditions, and they will be homogeneous Neumann everywhere except for the left, where it is homogeneous Dirichlet. And we can do that as following. So we can enforce these boundary conditions quite easily. Let's take a look at our staggered grid. So we now want to set the values that are in these ghost cells just outside of the domain. And let us start again at the left with the inlet. And if we want to have a Neumann boundary condition, we are setting the... So now if we want a Neumann boundary condition, then we have to get the derivative over the boundary. And for this, we just take the value outside of the boundary minus the value just inside of the boundary divided by the cell length, which is the distance between these two. And this one has to be 0. And then that means in order to get the 0 derivative, we need the negative of the inside just at the outside. So let's translate that into code, and let me go down to our point here by saying pressure correction in next, and then we take interior in y and 0 point in x direction is going to be pressure correction next, interior in y, and then 1 to get our interior point here. Then for the right side, for the right edge, so we have pressure correction next, -1. And here, remind yourself, we want to use a Dirichlet boundary condition. So we want to take the average, and so we say outside plus inside over 2 has to be equal to 0. And this consequentially means that the outside value has to be the negative of the inside value. So let me go down here and say this one is the negative of the inside value. And then we have to also make our update for the top and the bottom, which will be 0 and colon. And here we just do, this is going to be 1 and colon, and pressure correction next at -1 and colon is going to be pressure correction next at -2 and colon. And then we have to make sure that our smoothing makes progress. So we will advance in smoothing, which basically means we say pressure correction previous is equal to pressure correction next. And after 50 iterations, we have found a pressure correction. And in these projection schemes that we are using, these pressure corrections are used in order to enforce incompressibility. So they locally correct the pressures such that we don't lose any mass. But first, with our pressure correction, according to the algorithm, we're going to update the pressure. So this is step number 5. So here I want to say update the pressure. So we say pressure next is going to be pressure previous plus the pressure correction next. And then we can correct the velocities to be incompressible. And in order to do that, let's look at the algorithm. So we say that the projected velocity is the tentative velocity minus time step length multiplied with the derivative of the pressure correction. So this is important, not of the pressure itself, but of the pressure correction. So we will take this derivative first for x and y direction, and then we can update our values. So let's go down here and say the pressure correction gradient in x, and this one is then going to be similar to what we've done with the pressure gradient in x. So we're going to have that pattern here. And let me just copy that by saying pressure correction next, interior in y, and 1 forward in x direction, but not to the very last element, minus pressure correction next, interior, and then 1 to -2. And I see that is not how I usually do that. So let me fix that. And then we can divide by the cell length. And again, we only need 1 times cell length, because this is just how our staggered grid is laid out. Then we have a gradient in y direction, and this one works also similar to what we've done with the updates in the y direction. Similar pattern, we do the pressure correction, and from 2 to -1, and interior in x, minus pressure correction next, 1 to -2, interior in x. And here we divide by the cell length. And then we can use these two gradients to update our velocity. So I will go here and say that velocity x next at the interior is going to be the velocity x tentative at the interior minus the time step length multiplied with the pressure correction gradient in x. And here we don't have to select the interior because we just computed a gradient only for the interior values of our x velocity. And we do something similar in y velocity direction. So velocity y next at the interior is going to be velocity y tentative at the interior minus the time step length multiplied with the pressure correction gradient in y direction. And we're almost done. Last steps, bear with me. We have to again enforce the boundary conditions. Again enforce BC. But for that, I will just copy this. So here we have the velocity in x boundary conditions. So I will first copy both of them down. So get me the y velocity as well. It's because they do not change in the way they are prescribed. They are just now prescribed on the velocities next. So let me just batch rename that here and say this one is velocity x next. And then here we also have velocity x next here as well. That's a little bit tiring. So let's do something similar here and say velocity y next. And then also this one, yes, should be fine. That's a little bit boring to watch, but now it should be done. This is then the end of step number, I think it was 6, yes. And now we have this repeat, and we will just say that the previous is going to be the next in order to advance in time. So let's say advance in time, and the velocity x previous is going to be the velocity x next. The velocity y previous going to be velocity y next. And, sorry, pressure previous is going to be pressure next, such that we also have a fresh pressure gradient in the next iteration. Then we can finally turn our attention towards the visualization. So let's say visualization. And for this, we first want to check if we are in a time iteration where we also want to visualize. So if iteration modulo plot every is equal to 0, then we also want to visualize. And then remind yourself that we have the mesh vertices as coordinates, but our velocities, that's the one we want to visualize, are staggered. So we will just move them to the mesh vertices by averaging. And we can do that for the x components by averaging in y direction, and for the y components by averaging in x direction. So I want to call this velocity x vertex centered instead of staggered. And this one is then velocity x next at 1 all the way to the end, and then all points, because we now also want to include boundary values. And here we need a plus now, velocity x next 1 to -1. So let me adjust a comma here, and then colon and divided by 2. And for the velocity in y direction, as said, we are averaging over x. So velocity in x or velocity y vertex centered, similar thing, velocity y next, all points in y direction, and then 1 to the end, plus velocity y next, all points, and then all the way to the very last element, excluding it, and then divide by 2. Then let's first create a contour plot to get a feeling for what is going on. So PLT contour F, and for this we need the coordinates in x, coordinates in y, and for the start I want to use the velocity x vertex centered here, and I want to use 10 levels, and for the color map, as said, I want to use the one from this CMeasure package, and the one I want to use is called Amber, and I will want to set the minimum value at 0 and the maximum color value at 1.6. And then we have to interactively draw that, get some pause in here of 0.05, and then plt.clf to clear the figure. And if we haven't made any mistakes, which is, well, the chances are quite high we did, but anyways, let's check, and then we have to debug them in case. So let's execute that. And now, interestingly, actually it runs. That's quite nice. And we also see that it is like almost getting to where we want it to be. So it's creating this pipe flow that we were expecting with the boundary layers. Maybe we want to make that a little more visual. So let's maybe increase the time step length to 0.3 here, and then let's run it again such that it goes a little faster towards where we want it to be. And yes, here now it works. That is where I want it. Yes, and you also see that there are like these more layers now coming in, and you see the boundary layer happening here, but it's not the final visualization. So let's make it look like it was in the intro. First, right before the time loop, I want to set something regarding the styling. So let me say plt.style.use dark background, because dark mode is always nice. And then let's create a figure with the following aspect ratio. Fig size is 1.5 times aspect ratio and 6, which actually is not the correct aspect ratio, but it just looks nice, and we can like mentally account for the distortion rate. So let's go down here, and if we let this run again, we should be getting, yes, like what we've seen in the intro. Amazing. Maybe it would be also nice to have a color bar here next to the plot. So let me close that down and add a color bar. Then maybe on top we can lay the quiver plot, so the vector plot. So let's do plt.quiver with coordinates in x, coordinates in y, velocity x vertex centered, velocity y vertex centered, and just let me decrease the transparency to 0.4 for the one that we want to put on top. So if we run that, we should have, yeah, well, a quiver plot, but maybe a little too many points in there. So let's reduce that. I will close that down real quick and just only select every 6th entry in x direction. So I do all entries in y direction, but only every 6th entry in x direction. And that's also what we have to do here. And here as well. Hopefully that should make it less cluttering. Yep. And yeah, and I think you should be able to see that the velocity vectors at the top and the bottom, closer to the boundary, are getting smaller, whereas the one in the center are getting larger. And we also see that we have some downwards pointing velocity here. That is because from the inflow pattern, which is uniformly over the axis downwards, we see that the flow has to go down a bit. And let me also add a plt.show in the very end so that our plot keeps running. And maybe I want to increase the time step even higher. I think we should be good to go to 0.001. And let me run it again. Yes, that's also now way faster, and we don't have to wait so long in order to get the almost steady state. But I also want to show one more thing, that the distribution of the vector, or like how they are pointing in x direction, is actually this hagen-poiseuille parabolic profile. Oh, by the way, now you see we have reached the steady state. The solution does not change anymore, but let me close that down. And in order to get this parabolic shape, I will just lay some line plots over what we already have here. So I will do plt.plot for a simple line plot. And for this, you usually would plot y over x. But since we want to have the parabola kind of like aligned with our cross-sectional axis, if you say so, then we have to plot y over x. So I want to plot the velocity in x vertex centered over all points in y, and the 5th point in x direction, and the coordinates in y over all points in y direction, and the 5th point in x direction, which is just slightly behind the inlet. Or maybe let me also put that in the new line. I want to use as a color black, and I want to do a line width of 3. Let me put that here. And then let's run it again. And here we see our flow profile, and we see that it's not a parabolic shape. It is already showing us that the flow is, yeah, almost zero or like getting to zero at the boundary, but it is still not this clearly parabolic shape. And that's because we are just slightly behind the inlet and it takes some time for the flow to develop. So let's also plot it at other points here. And in order to move our parabola a little bit more towards the right, I want to add something in x here by saying 5 times the cell length added to this value. This just moves our parabola a little bit to the right. I think you should be able to see that here. And now we can use this to plot some more. So let me do 2 more, and I want to have one at 20 discretization points in, and another one at 80, because the one at 80 in our current configuration should be sufficient to already get the fully developed flow pattern. So let me run that. And here we see, yes, that's the flow pattern we want here. So just to explain it a bit, here as said, we don't have a full parabola yet. Here we are getting closer to it, but it's not there. But also if you look at the contour lines, then at maybe approximately here, or a little bit, here, they are now parallel to each other. And that means that, we don't have a gradient in that direction. And this then also means we get this nice parabola here. But there is one more thing we have to account for, because it is really important to have our equations conserve mass, which is the constraint on the incompressibility that we have here. And we are doing that locally with our pressure correction scheme, but we also have to do that globally, because everything that enters from the left has to exit from the right, and actually at the same mass flow rate. It might have a different flow pattern, and it has. It changes from the uniform pattern to the parabola pattern, but if you were to integrate the pattern on the left, the value should be equal to the pattern on the right. And we can check on that by going right before our visualization and calculating the inflow mass rate. So inflow mass rate, and for this we will just sum up the values at the very left. So we do velocity x next at all interior values and then point 0. So this is the inlet. And then we can define the outflow mass rate by using a -1 instead. Then let's print that out by saying inflow is the inflow mass rate, and then the outflow is the outflow mass rate. So I'm using here some format strings and just a new line. This will be a little bit messy now, but it should print it out. And here you see the mass flow rate, or at least the approximation of it, is 14, whereas the outflow rate is not always 14. So it is trying to correct that a bit, but it's not yet where it should be. I mean, it's approaching that. That's super interesting. But it should conserve that theoretically at each step that we have here. And we can make that conserve it by multiplying the value that we set at the outlet with the ratio of inflow to outflow. Let me use these values that we have here, inflow-outflow mass rate, again when we prescribe the boundary condition. So let me do inflow mass rate next and outflow mass rate next in order to assess the point at this next time step. And we can maybe also call that one next here then. And in order to then conserve mass, let's move these two right here, right above, to where we set our outflow boundary condition, and then multiply that with inflow mass rate divided by outflow mass rate. And then we should conserve that somehow. And of course, that is a mistake. Of course, we should take the value at -2. because if we take the value at -1, we would be summing up over zeros, because that's the initial condition for our next velocity. But here this should be this one, and let's see. Still not as correct because it's still showing this other value here, but we can then calculate it once again. And then of course it should ensure that. So let me copy that down again and see here. So let me run it again. And now it should be, and of course we need to go back to the -1 here to be at the very end. And then we should be good that the mass is basically conserved here. And here we see that it has only a minor influence on the flow pattern, because earlier the problem there, or the difference, was not too high, but it is usually a thing that you have to do also in more complicated pipe flow scenarios in order to ensure that your incompressibility will hold. So then let me close that down and comment out these printing and computation statements, because they are rather cluttering. And let me run it again. And here we see how our patterns are creating again beautifully as it was before. Let me close that down and address one last thing, which is the stability of our algorithm. So if we go all the way up, I left some notes in the source code file here. And in case you want to play around with the parameters, be aware that due to the fact that we're using explicit time integration with the diffusion, we have an stability criterion that we have to meet in order to be stable from the diffusion side. And due to the fact that we have a nonlinear contribution in the convection, you might have to include some additional safety factors. So even if you were to hold this condition, it could still become unstable. And also be aware that if you reduce the kinematic viscosity to super low values, then you could run into trouble that you're using a central differencing scheme in the convection, because at some point your Reynolds number might go higher, and then you will have a convection dominated flow. And in the worst case, you might even get Reynolds numbers which lead to turbulent flow, and then our simulation here will no longer be accurate. And another point, the Jacobi smoothing that we do in the pressure correction problem is just a simple approximation, and we are not even checking for the residual to see how good we've solved the system of equations there. So in case you want to use that for anything more sophisticated, you probably have to adapt that. Then let me run the script one last time to finish off the video. Here in this one, we implemented the transient pipe flow scenario with an inflow at the left, an outflow at the right, and wall boundary conditions at the top and the bottom, such that we see the boundary layers creating as well as the hagen-poiseuille profile. You find the source code on the GitHub repo of the channel, as well as linked in the video description, and I would encourage you to play around with it, change the parameters, make an extension of it. I would be happy to see your pull request on GitHub and share it with the wider audience. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. If you enjoyed this long video and stayed all the way to this very end, I'm super proud of you, good job, and I hope you kept your sanity with all the staggered grid action here. I think this will get easy over time. It just has some steeper learning curve because it's rather unnatural to stagger these values. By the way, you also don't see that in commercial CFD software. They all use co-located grids with these Ryu-Chow correction, but they by themselves, these corrections, can become also a little bit nasty. Anyways, if you enjoyed this video and want to see more of that content, then please hit the like button and consider subscribing to the channel. I would extremely appreciate that. Here, in the very end, you now see similar videos as well as the playlist for other simulation scripts. I would be happy to see you in another video.